Hey class, this is Juan Ramirez with EE 2725, Linear Circuits 3 AC, and today we're going to cover how we apply Thevenin and Norton's theorems to phasors in AC circuits. And this is part of chapter 10.6 in the Fundamentals of Electric Circuits book. So the first step, or sort of point to make, is the one that we've heard before, which is that these theorems that we've learned already, such as Thevenin and Norton's theorems, they apply to phasors in AC circuits the same way they did in DC circuits. The difference is that now you have a complex number instead of all real numbers. Okay, so let's first take a quick review of Thevenin equivalent circuits and Norton equivalent circuits. We'll go over the steps, and then after that we'll go and do a couple of examples. We'll do an example and apply the Thevenin equivalent circuit or Thevenin's theorem, and then we'll do the second example and apply Norton's theorem. Okay, so Thevenin's theorem and the equivalent circuit is a way to take some arbitrary circuit and some arbitrary circuit applied to a load and convert that into three simple components. Obviously, that arbitrary circuit has to be linear. But if we do have this arbitrary linear circuit, we could convert it into an equivalent voltage source with a series impedance. So we just converted this potentially complex circuit applied to a load, converted that into an equivalent series voltage source with a series impedance, again connected to that load. And note that our load is now an impedance and not just a resistance or a combination of resistive elements. Okay, so what are the steps we take? The first one is to find the Thevenin voltage. Oh, sorry. Okay, so to find the Thevenin voltage, we find the open circuit voltage at the load terminals with the load disconnected. So you take off the load and just leave those terminals open, and you find that voltage across those terminals. That's your Thevenin voltage. To find that open circuit voltage, you could use any of the other circuit analysis methods, such as nodal analysis, mesh analysis, superposition, voltage division, current division, Ohm's law, etc. I will say, however, there's a tendency of nodal analysis being the easiest way to find a Thevenin voltage or an open circuit voltage. For the second step, we have to find the Thevenin impedance. And that's simply the equivalent impedance at the load with the load disconnected. So we're going to remove the load. We're going to turn off all our sources. By this point, we should remember how to do that, which we do by replacing a voltage source with a short circuit, because if you're turning off the voltage source, it means the voltage is zero, and a short circuit, by definition, has a voltage of zero. And to turn off the current source, you replace it with an open circuit, because an open circuit, by definition, has zero current. And turning off a current source means there's zero current. And finally, you will want to find the equivalent impedance. And that is how we apply Thevenin's theorem. Those are the steps. So now let's go ahead and do a similar approach for Norton's theorem. So in a similar way, Norton's theorem is a way of converting some potentially complex linear circuit attached to a load into an equivalent current source called the Norton current, a parallel impedance called the Norton impedance, and that load. And I do want to kind of clarify that load. It could be one impedance, it could be a network of impedances, it could even include voltage sources and current sources. Okay, so I'm representing it all with just that, but just remember that it could be more than just an impedance. Okay, so now what are the steps we take for Norton's theorem? The first step is to find the Norton current, which is the same as the short circuit current at the load terminals. So here we're going to replace the load with a short circuit and find the short circuit current through those load terminals, through that short. Okay, and again, The Norton current is that short circuit current. And then for the Norton impedance, it's actually found the same exact way as the Thevenin impedance was found. So we simply remove the load, turn off sources, and find equivalent impedance at load terminals. Okay. Now, let's do a couple of examples. All right. Let's use Thevenin's theorem to find V out. And we're going to actually analyze a circuit that we've looked at before. Kind of like doing that because it assures us that these methods really work, right? We're getting the same answer with each of these methods that we're assessing and applying. Okay, so V out is the voltage across that 2 ohm resistor. So what I'm going to do is I'm going to call that 2 ohm resistor, that's going to be my load impedance. Okay, so that's our load. So now we're going to find the Thevenin voltage. So I'm going to say, step 1, find open circuit voltage, which is the same as the Thevenin voltage. And to find this open circuit voltage, you actually remove the load, the 2 ohm resistor, and you look for that voltage across those terminals. So what's the best way to do this? Honestly, you could use nodal analysis, but you could also just use KVL, because I do want you to notice one thing. I'll draw it in green. If you take a look at this node here, how much current is flowing here? Let's call that I. Now little I, that's equal to 0. Why? because there's an open circuit. Right after that capacitor, there's an open circuit. There's nowhere else for that current to flow. Therefore, no current could be flowing through that capacitor. While an impedance follows Ohm's law that says voltage across an impedance is equal to current through the impedance times the impedance value, right? And that's Ohm's law for AC circuits. And so if the current is equal to 0, then the voltage across it is equal to 0. So all that to me means that if the voltage across a capacitor is equal to 0, then the voltage across these 2 points has to be VOC, right? From the top of that inductor to the bottom of that 12 volt source. Okay. The only other thing that I noticed is that because no current flows through that capacitor, then all the current has to flow in a loop like this. I'll call that loop big I. That'll be the loop current. Now let's do KVL. So let's say we're starting at this bottom right corner, and we follow that clockwise convention of current flow. So you have a voltage rise of 24 volts. And we've had enough exposure to this that we know that a polar form 24 volt amplitude 0 degree phase is equal to a real 24 volt in rectangular form. Minus the 2 ohm impedance times I, minus the J2 impedance times I, and then plus 12 for that other voltage source. Okay, and now we're going to solve for I. So I can do this minus 2 minus J2 I, and then I can move 24 plus 12 is 36. I can move that to the right. And then I can solve for I. Okay, and now that we have I could find out the voltage across the J2 impedance, and that'll tell me the open circuit voltage. So the open circuit voltage, which is also the Thevenin voltage, is equal to negative 12, because of the polarity, plus J2I. That's equal to negative 12 plus J2, 9 minus J9. Do some math and you'll find out that it is equal to 6 plus J18 volts, which is equal to 18.97 with a 71.6 degree phase margin. And that's our Thevenin voltage. Now let's take a look at Thevenin impedance. So to find that Thevenin impedance, you have to find the equivalent impedance at the load after turning off all sources. So I turn off that 24 volt source. I turn off the 12 volt source. And I analyze the circuit at the load terminals. Okay, and the Thevenin voltage is going to be equal to the 2 ohm impedance in parallel with the J2 with the inductor, and then that in series with the negative J2 capacitance. And when you work that out, you should get 1 minus J in ohms. So our Thevenin equivalent circuit looks like this. This is what it looks like. 18.97 volt with a 71.6 degree phase angle. That's your Thevenin voltage. The series impedance, which is called the Thevenin impedance, that's 1 minus J ohms. And then our load is what we had originally pointed to as our load. That's the 2 ohm resistance because we're looking for the output voltage or V out across it. So that's our Thevenin equivalent circuit. Now we actually have to find V out. But V out at this point is pretty easy to find using voltage division. Using voltage division, V out is equal to that source voltage across both of the series impedances. One second. All right. Sorry for that quick break. Okay. So voltage division again to find that V out. You multiply the source voltage across the series impedances, and then you multiply that by the impedance that you're looking for the voltage across in the numerator, divided by in the denominator the sum of the series impedances. Okay, if you work out the ratio of impedances, you should get 0.63, 18.4 degrees. And when you do that multiplication, you get 12 volts with a 90-degree phase angle. Which is what we got last time. All right. Now let's take a look at the same example again, but using Norton's theorem. Okay, so again, I'm going to draw the circuit. Okay, step one of Norton's theorem, and also, again, of course, the load will identify to be the 2 points, that are across that 2 ohm impedance on the right, since we're looking for the V out, or that output voltage at that point. So that's your load. Step one, we're going to look for the short circuit current. Which is the same as the Norton current. So that's when we take off that load impedance, in this case the 2 ohms, and we'll replace it with a short circuit. And we'll look for the current through that short circuit. Now instead of leaving that as an open circuit, I'm going to just draw a line between them, and that's my short circuit current. Okay. The best way, in my opinion, to find the short circuit current is to use mesh analysis. So this is kind of a good example for mesh analysis. So we identify the 2 meshes, and we apply KVL at each mesh. And then you solve, and ultimately the short circuit current will be equal to mesh current 2. So KVL at mesh 1 will be 24 minus 2 I1 minus the J2 impedance that shares the current between I1 and the opposing current I2, and then plus 12. We could do a little bit of simplifying. Okay, so I kind of expanded on the negative J2 times I1 minus I2. Expanded that, combining like terms to get negative parentheses 2 plus J2 times I1 plus J2 I2 is equal to negative 36. That's our mesh 1 KVL equation. Let's take a look at mesh 2. If we're starting from that bottom left point, now we have negative 12, then minus J2, and now it's I2 minus I1, because now we're kind of looking at it from the mesh 2 perspective, which is that I2 is positive and that I1 opposes it. And now we're going to have a voltage drop across that capacitor, but the impedance of the capacitor is negative, so it'll be minus negative J2. Okay? And then obviously the short circuit, there's no impedance there, there's no voltage drop because of that. So again, we're going to combine like terms. And actually something you notice when you're doing this is that you end up with negative J2I2 plus J2I1 plus J2I2 equals negative 12. The J2I2's cancel, which is nice. And so you could use the KVL equation at mesh 2 to actually solve for I1. Alright, and we get negative J6. Sorry. This is positive 12. Okay, that's I1, but we actually really care about I2, so let's plug that back into the first mesh equation. So first mesh equation into the second one into the first. So we have negative 2 plus J2 times negative J6 plus J2I2 is equal to negative 36. And now we're just going to solve for I2. So what do we get? We get J12 minus 12 plus J2I2 is equal to negative 36. Move the J12 minus 12 to the right and divide by J2. And you get negative 24 minus J12 all over J2. That is negative 6 plus J12. And if we convert that into, and that's in amps, convert that into polar form, it looks like this. And that's I2, which is also equal to our Norton current, which is equal to our short circuit current. Okay? That's step 1. Step 2 is to find the impedance. So that equivalent impedance will be what we call the Norton impedance. It turns out we do it the same exact way we did it for the Thevenin, Thevenin's theorem. So again, we're going to kill that 24 volt source. We're going to kill that 12 volt source. And we're going to look at the impedance from the load terminals. And we can just write what we got from last time, which is 1 minus J. So now we can write out the Norton equivalent circuit. Alright, so to do that, we're going to take a look at our Norton current, which we found in step 1. In parallel, we'll connect the Norton impedance. That's the difference between Norton equivalent circuit and Thevenin, is that Norton has a current source, and in parallel it has that equivalent impedance. Thevenin had a voltage source, and in series it had that equivalent impedance. And then we connect it again to that 2 ohm load. Okay, well, what you typically do with a Norton equivalent circuit is you do current division, kind of like we did voltage division for the Thevenin equivalent circuit, as a last step to find your output voltage or current into your load. Here, however, if we do current division, we find the current going for the 2 ohm resistor, and then we simply multiply by that impedance to find the output voltage. So one extra step after that. So that current through the 2 ohm resistor will simply be the source current going into the parallel branches times ratio of impedances where the numerator is actually the opposite impedance to the one you're looking for the current at. And the denominator will be the sum of them. This is the case for current division having 2 impedances. It's actually a little bit more complex when you have more than 2 impedances, and you'll just have to go back to your current division notes to take a look at that, but essentially you'll look at the inverse of those impedances. And when you do that, you end up with 6 amps with a 90-degree phase shift. And we said the V out, or V0, is equal to that current times the 2 ohm impedance. The 2 is real, so it just multiplies by the amplitude and gives you 12 with a phase angle of 90 degrees. And that's exactly what we got in our last analysis and also in the previous examples we've covered. Previous iterations of this example using different approaches. So it works. And I do want to cover a couple more tips. The tips are for the evidence theorem, and I kind of alluded to it throughout, nodal analysis is typically easier to find the open circuit voltage. I'll also say, remember, no current flows through an open circuit. So when you're doing that analysis of your open circuit, no current flows through the open circuit. So if there's a series impedance with your open circuit, there's no voltage drop across it. And for Norton's theorem, kind of the same type of tip. Mesh analysis is typically easier for finding the short circuit current. The second tip for Norton's theorem, I think, is sort of intuitive, but also easy to forget. Once in a while, your load will be in parallel with some other impedance. And when you're going to apply a short circuit to find that short circuit current, you'll have a short circuit in parallel with an impedance. Just remember that a short circuit in parallel with an impedance will nullify the impedance, because a short circuit has an impedance, theoretically, of 0 ohms. That 0 ohms nullifies the other one. If you take 0 in parallel with anything that's not 0, or anything that is 0, you end up with 0. Okay? So, also remember, a short circuit in parallel with an impedance will nullify it. Okay, and let me give a quick example of that. Say you have a circuit like this. I'll do a quick example. Say you have a circuit that looks like this. Okay, and you have some values. Okay, so you have the circuit, and they say, hey, find I0 using Norton's theorem. Well, the first step of Norton's theorem is to find that short circuit current at the load terminals. So the correct thing to do would be to replace the 1 ohm resistive load with a short. Sorry. My point here is that you now have a short circuit in parallel with that capacitor, that capacitive impedance. Please be aware that the impedance of the short circuit is 0. So 0 in parallel with anything is going to be equal to 0. All the current will flow through the short. Okay? And if you want to really think about the reasoning, if the short circuit has an impedance of 0, regardless of what the current is, what's the voltage buildup across it? It's going to be 0, right? V is equal to IZ for AC circuits. And if Z is equal to 0, then V has to be equal to 0. Right? Z goes to 0, so does V. But they're in parallel, so they have to share the same voltage. So if there's no voltage across the short, there's no voltage across the capacitor. Well, if there's no voltage across the capacitor, according to V equals IZ, I has to be equal to 0 for that capacitor. So sort of by putting 2 and 2 together, you determine that no current will flow through that capacitor, and it essentially behaves as if it didn't exist, if there's a short circuit in parallel with it. So I just wanted to kind of hammer that home and make sure that was clear to you all. So those are the 2 tips. And yeah, please practice some on these. I know Thevenin and Norton's theorems could be a little bit awkward, but practice makes perfect, and I think making sure you maybe apply both theorems on the same circuits as you do examples, that's always pretty helpful because you're able to look back and forth to make sure that you get the right answer on both. Alright, thank you very much for watching.